In this module, you'll learn the power rule, which is a fantastic shortcut for finding derivatives. But to really appreciate it, first you have to see just how difficult derivative finding is without the power rule. So, as I said in the last module, you can find derivatives using the difference quotient. Let's go ahead and do that. We're going to find the derivative of f of x equals x squared using the difference quotient. So I should plug x plus delta x into the function x squared, and then to subtract x plugged into x squared. So let me do that. Now we need to simplify.
This is all review, so you can skip this part if you don't need it.
And I'll get x squared plus 2x delta x plus delta x squared minus x squared all over delta x. You can see why the difference quotient is a little complicated. We've got a lot going on here. So let's go ahead and cancel those x squared terms out. And now we're going to use the factoring method to evaluate this limit. In other words, we're going to factor out a delta x in the numerator and then cancel it with the delta x that's already in the denominator. We can now plug in 0 for delta x to get the limit and our derivative answer that we've been looking for the whole time. The answer is 2x. So in other words, the derivative of f of x equals x squared is f prime of x equals 2x, according to the difference quotient. There has got to be a better way than this. And there is. The power rule. And since you've seen the ugly way to get the derivative, you'll appreciate the easy way even more.
And this is the new stuff. Start with this.
As I said before, the power rule is a shortcut for finding very simple derivatives. If you've got a variable being raised to a power, then you can use the power rule to find its derivative. I'll show you how to do it with x squared, since that's the derivative we just found a second ago. There's two steps we need to follow here. First, pull a copy of the power down in front of the term. So in x squared, we're going to pull that power of 2 down in front. Next, subtract 1 from the exponent. Here, my exponent was 2, so I'll subtract 1 from it. 2 minus 1 is 1. And that's all there is to the power rule. The derivative of x squared is 2 times x. Remember, we don't have to write the 1 power, because if there's no power written, it's understood to be 1. Can you see why this is so much easier than the difference quotient? It even works if the term you're differentiating has a coefficient to it. For example, let's derive g of x equals 3x to the 7th power. Before we apply the power rule, we'll just scooch the 3 over a little bit to make some room. Now, all we have to do is pull a copy of that 7 power down in front, subtract 1 from it, and we have 3 times 7x to the 6th power. To finish, multiply 3 times 7 together and get 21. One of the most powerful and one of the most basic rules of calculus. The power rule is great.
Along with other stuff that goes with the power rule, here's my notes on it. One thing you should know is that the derivative of a constant is 0. So that's what this says up here. Derivative of a constant is 0. Also, here is the power rule. Derivative of x is 1. Okay, because then x goes to 0 power, and that's what we got. So, just wanted to let you know. All right, here's some problems. We're going to do some problems together. Find the equation of the tangent line of f of x equals x squared when x is negative 2. All right, whenever you have something like this, first you want to find the derivative. So the derivative, or f prime of x, now is equal to 2x. We have the x. We want to plug this negative 2 in for x. So at that point, f prime at negative 2 is negative 4. And now point slope, right? Well, we don't have the y value. So we have to get the y value. To get the y value, y value is always plugged into the original. Plug into the original. You want to plug it into the original to get the y value. So the point negative 2, 4 is the point I'm looking at. Now I can do point slope. Because anytime you want a point, it's always the point on the graph. So I get y minus the y value, which is 4, equals the slope, negative 4, times x. I want to change colors there. Oh, no! No! I'm melting. Okay, here we go. All right, let's make it nice. All right, we're back. Okay, so, and then you take the slope, which I wanted in red, and then I want to go back to the black and do x minus the x value. So when the smoke clears, I'm going to get, that's fine. You know what, I'm not going any further. That's good as far as I'm concerned. I think it becomes, if you put it in the other way, it's y equals negative 4x minus 4. If you want the mx plus b form. I told you, this form is beautiful. All right. Let's get some derivatives here of some crazy trig, oh, they're not crazy, but some trig functions. These are ones that usually students memorize. So the derivative of sine is actually cosine of x. Derivative of cosine is negative sine x. A teaching strategy or a learning strategy is when you're taking derivatives, if I go to the sign has an I, and the negative in front looks like a sideways I. So that's the way I remember it. Stupid, but that's the way I do it. This one's going to be, just take the 1/2 out. So y prime is going to be equal to 1/2 cosine of x. Or you can put cosine x over 2. Doesn't matter. This one, I'm going to take derivative of both of those. All right, which you can do. So we're going to get, when we take the derivative, wow, my pen's not working today. Y prime equals 1 minus sine of x. 1 is the derivative of that, and negative sine of x is the derivative of that. So there are some trig functions for you. Now, if the derivative is rise over run, that's a rate of change. So anytime you have a rate of change, it's the derivative. So if I want to look at average velocity, that's speed over time. I want to, for example, drop a ball from 100 feet. And that'll be defined, the position function. S would be the position function. Position is always S. As negative 16t squared plus 100. 100 is the initial height. And negative 16 is because it's the 1/2 gravity. And gravity is negative 32 feet per second. So we're dealing with feet here. So now what I want to do is if I wanted to find it from, let's say, 1, 2 to 1, or I should say 1, 1.1. All right, so we want to find what the rate of change is between them. What we're going to do is I'm going to use, basically I'm going to put 1 in for t. Okay, so I'm going to get 84. Almost like slope. Okay, I'm going to use I'm using actually the alternate form of derivative. So I'm going to be 1.1 minus 1 on the bottom to keep it positive. So now I'm going to use 84 when I put in, actually 80, I'm sorry. I am very sorry. Oh, again with the big eraser, damn it. All right. It's going to be 84 when I plug 1 in for t. When I plug in, is that right? Yeah. And when I plug 1.1 in for t, I think I get 80.464. Subtract them. Let's get this guy out of the way for now. And we're going to get, no, I screwed this up. I totally screwed this up. I screwed this up. 2 different problems. Sorry. I'm doing 2 different problems. Alright, so we're going to do this problem. We're going to put 1 in, we're going to put 2 in, and do it the same way as I just said. So it's going to be 2 minus 1. When I put 2 in there, I get negative 32. Negative 32, and no, that's wrong. It's 2 squared, which is 4. 4 times 16 is, I don't know, you're testing me. Maybe 54, 64, 64. 64, so that's 36, and when I put 1 in, I get 84. So then at that point, 1, 2, all right, it's negative 48 feet per second. You might say, why negative 48 feet? Well, it's going down. Anytime you're going down in physics and in mathematics, it's negative. Now let's try a smaller interval. like 1 and 1.1. So I'm going to do 1.1 minus 1. Well, I know for 1 it's 84. For 1.1 it's 80.64. 80.64. So that's going to be negative 33 feet per second. And it makes sense because the velocity, the average velocity, if you go from 1 second to 2 seconds, it's got to be getting faster going down than 1 to 1.1 seconds. Makes sense. Here's instantaneous velocity. And basically what I'm saying is instantaneous velocity is a derivative of the position function. That's all it is. The last type of problem we're going to look at is a problem that you see in the free response questions with calculus and physics, or the physics version of calculus, or vice versa. That deals with something being thrown or something like that. This time we have a diver jumping off a diving board. It's 32 feet above the water. Okay, we just watched the Olympics, so we've seen this. And the initial velocity is 16. Two questions. A, when does the diver hit the water? And B, what's the diver's velocity at impact? So I'm going to use 32 feet per second for gravity, throw it in there, and my position function for A, I'm going to solve A right now, and my position function for A now is negative 16t squared plus 16t plus 32. That's equal to 0, and remember that's my position function. Now, I just want to solve it. I don't need a derivative because I just want to know when it hits the water. When does it hit the water? I'm solving for time. So if I factor out a negative 16, I get t squared minus t, come on, minus 2 equals 0. Just keep on factoring. Factor, factor, factor. T, I guess this is minus 2, and then t plus 1 equals 0. So I guess I get my answers of 2 and negative 1. You can't have a negative 1 time. Later on in calc you'll see you can, but right now you can't. So we're going to say for A, they hit at 2 seconds. It takes the diver 2 seconds to hit the water. That's part A. Part B says what's the velocity at impact? All right. So now what we have to figure out is the derivative at impact. So we're going to find out, we know it takes 2 seconds to do this. So we're actually going to look for the derivative at 2 seconds. Well, if I take the derivative of this thing, I get negative 32t plus 16. All right. And now I'm just going to plug 2 in there. So this is the derivative. Plug 2 in there, and you get negative 48 feet per second. That's the velocity of the diver at impact. Hope you did all right. Like I said, when does the diver hit the water? That's just solving for time. And velocity is taking the derivative of the position function. All right, you'll do more for homework. Have a good day.